Welcome to the deep dive. Today, we are looking at a really complex problem, one with massive strategic implications for Australia. We're talking about the sustainment report for the Royal Australian Navy's Canberra-class LHDs. These are huge, essential ships, really the core of Australia's ability to project force, and the sources you've shared with us reveal they are in serious trouble.
They are. And what makes this particular deep dive so interesting is the source material we have. It's not just a standard audit. We have an analytical report that goes way beyond the usual findings from, say, the Australian National Audit Office. It actually applies a mathematical framework network science to diagnose the failure mechanism itself.
Okay, so that's the hook. That's where it gets fascinating. Our mission today is to unpack not just what is failing with the maintenance on these ships, but the mathematical reason why. Why are relatively small budget constraints causing these massive strategic gaps in capability? And let's just, start with the headline finding, because it is genuinely shocking. These two critical vessels are basically operating as a one-ship force.
That is the hard reality.
Yeah.
The Navy's target for platform availability, that's the time the fleet should be ready to go, is 80%. What we're actually seeing is availability stuck at, 55 to 60%. And this is all down to a staggering cumulative backlog of 223 urgent defects. That's the physical result of maybe 7 to 10 years of deferred maintenance.
And the root cause here is the crucial thing to understand. It's not the usual story of incompetence or bad management. This report points its finger directly at chronic structural underfunding. And this isn't a new problem. It goes all the way back to the acquisition phase from 2007 to 2016.
Exactly. And the real aha moment in this whole analysis is how they quantify that failure. I mean, in a normal system, you'd think a 10% budget cut leads to, a 10% loss in capability? But this analysis found that because of how these complex systems are wired, a mere 10% budget shortfall triggers a devastating 30 to 50% loss in platform availability.
Wow. That nonlinear amplification, that multiplier effect is really what we need to get into today. Before we dig into the network science that explains the why, let's start with the hard evidence, the stuff laid out in that ANAO audit report number 50.
Right. The NNAO report is foundational. It forces us to look past the easy answers. The audit went through all the structural responses. They looked at 3 different contracting models that were supposed to fix things: the transition model, the asset class prime, the maritime sustainment model.
Aim on and thread, none of them worked. And they failed not because the new management chart was wrong, but because the budget constraints just steamrolled any attempt at reorganization. The audit actually concluded they just created a more proficient path to inevitable failure. That is brutal assessment.
It is. It really is. And the numbers, they just lay out the deficits so clearly. Sustainment funding was going up by about 5.8% a year, which, sounds okay. But the actual cost of maintenance parts, labor, everything was escalating much faster at 8 to 12% per year.
So you have a 4 to 6% deficit every single year. That gap is just growing exponentially. You're falling further behind year after year. So what's the immediate result of that? On the deck plates, how does that show up?
It shows up as the deferral crisis. Because the budget was never enough, the only thing they could cut was maintenance. So we're seeing that 68 to 72% of all identified maintenance is just deferred annually. If you push off 2/3 of the necessary work every single year, you very quickly build that backlog of 223 urgent defects.
And we saw the government step in, right? An emergency injection of $300 million in 2024. Did that fix it?
It addressed the symptoms, the immediate bleeding wounds, but not the cause. The ANAO was explicit. They called that funding addressing symptoms rather than structural underfunding. And even after that huge one-time payment, availability is still stuck at that abysmal 55 to 60%. The core budget problem is still there.
So if you're delaying the work and you don't have enough money for the work you do approve, the timeline for those approved repairs must be getting longer and longer. What did the ANAO find there? And you mentioned RPRs and ECPs. Can you quickly break those down? Because the timelines are just shocking.
Of course. An RPR is a request for problem resolution. That's your standard repair, anything from simple to complex. An ECP is an engineering change proposal. That's a major systemic fix. A modernization, something that needs serious planning.
Got it. And the timelines?
They've blown out.
Right.
The average RPR now takes 840 days. That's up from 620, a 35% increase. And for those major engineering changes, the ECPs, you're now looking at up to 3.8 years, a 46% increase. That lengthening timeline just feeds the backlog. The fleet can never catch up.
And the source highlights another problem, a secondary one, but it's just as corrosive, the personnel gap, which is both a cause and a consequence of the budget strain.
It's a critical layer is the problem, yeah.
Right.
There's a structural shortfall of 40 to 60 organic Navy technicians. That's about 14 to 21% of what they need. And this forces them to rely on expensive private sector contractors.
And that cost difference is huge.
It's double. You're paying a contractor $150 to $200 an hour versus the internal Navy rate of about $90 an hour. So the original underfunding means they can't train their own people, which forces them to spend their limited money at a much higher rate. It's a classic vicious cycle.
Okay. So the ANAO audit documents all the symptoms, the underfunding, the deferrals, the exploding repair times, the workforce gap. But now we need to get to the diagnosis. This is where the network science comes in to explain why these symptoms amplify so much.
This is the key transition. The analysis models the LHD not as a ship, but as a complex system. It's made of over 150 subsystems, those are the nodes, and they're connected by 584 dependencies, or edges. This mathematical map lets you see the system's shape, its topology, and, critically, its resilience.
And that topology reveals the ship operates as a scale-free network. For those of us who haven't looked at graph theory recently, what does scale-free actually mean for a machine like this?
Think of something like the internet or the power grid. They all have this hub-and-spoke structure. Most of the components, the nodes, have very few connections. They're just peripherals. But a tiny number of central nodes, the hubs, are connected to almost everything else. New systems tend to connect to these existing stable hubs. It's a process called preferential attachment.
So in a system like that, you have robustness in most places, but this extreme vulnerability in just a few key spots.
Precisely. If a peripheral node fails, say a small cooling fan on a radar, the network is robust. The system barely notices. But if you have chronic deferred maintenance on one of those critical hubs, the failure doesn't stay local. It cascades. It spreads disproportionately across the entire platform. That is the fundamental weakness of a scale-free network.
Okay, so if the LHD is this giant scale-free network, which parts are the big critical hubs, the ones keeping defense leaders up at night?
The analysis found about 12 to 15 nodes with very high connectivity. But the top three are just absolutely vital. First, you have diesel propulsion with a connectivity degree of 18. Second is main power generation at 16. And third, the ship's brain, the combat management system, or C4ISR, at 14.
So to be clear, we're talking about the ship's ability to move, to provide electricity, and to fight. These three are the literal choke points for the entire operation.
They are the pillars of the system. And here's the core insight, the thing that explains the massive availability loss. Deferred maintenance on just these hubs, it accounts for only 15 of the 223 total urgent defects. That's just 6.7% of the total problem list. But when one of them fails, it directly triggers those cascading failures that lead to a 30 to 62% loss in platform availability. The budget is deferred on a tiny number of nodes, but the consequence is magnified exponentially.
That is the definition of a high-leverage failure point. Let's trace this out. Let's use the simulation sequence from the report to really visualize how one small issue in a hub becomes a systemic crisis.
Okay, we can walk through the 4 phases of how failure spreads in this chronic state.
Phase 1, the trigger.
This happens fast, usually within the first week. We simulate accumulated wear on a hub. Let's say it's a diesel engine. Because its preventive maintenance was deferred, it just fails, shuts down. The immediate impact on availability is tiny, maybe 3%. The ship is degraded, but it's still technically operational.
But it's a scale-free network. That missing capacity puts stress on all the other systems, which brings us to phase 2, the short-term crisis.
Correct. Over the next 1 to 3 weeks, the load gets redistributed, everything is running at max stress, the backup electric thruster kicks in. Power bus B, which normally has plenty of reserve, is now supplying 150% of its nominal load to compensate.
And there's the start of the cascade,
Right.
because that power instability is going to ripple out to everything connected to that bus.
Yep. Exactly. The combat management system, the C4ISR hub, starts getting voltage sag, intermittent signal dropouts. Now, this isn't just a glitch. This means the commander is getting unreliable data, maybe temporary blackouts on their radar screens. Their ability to actually fight the ship is suddenly compromised. Availability loss jumps dramatically to between 12 and 25%.
Now we hit phase 3, the full cascade. 3 to 4 weeks in, this is where the system starts to eat its own redundancy.
That's the perfect way to put it. Redundancy is depleted because everything's been running hot for weeks. Due to that sustained power instability, secondary systems, things like damage control, aviation support, they start to fail or become unreliable. The integrated sensor system response time increases by a dangerous 40%. The cumulative platform availability loss is now sitting at 30 to 45%.
And at this point, full operational capability is gone.
Unequivocally lost.
Yeah.
Yeah. The ship is now only good for low-intensity roles, like humanitarian aid. And even that might be restricted.
And phase 4 is the chronic state, stabilization at degradation.
Right. Without a massive catch-up program, the platform just gets stuck in this degraded state. The simulation confirms it. It remains at 30 to 45% availability because the annual $180 million budget is just not enough to fix the backlog. The failure is chronic because the chronic underfunding creates this self-perpetuating cycle of deferral and failure.
So the ANAO audit identifies the failure. The network model explains why the failure is so outsized. So how do we use this insight to propose a fix, and a fiscally neutral one? The goal wasn't just to ask for more money.
The key strategy is targeting the nodes that matter. The math showed that focused maintenance on those 12-15 hubs gives you a disproportionate gain, a 3x improvement in resilience compared to just a linear improvement from random maintenance. The solution is reallocation.
Okay, so the core proposal is Intervention 1, Hub Maintenance Prioritization. They propose allocating $36 million, 20% of the existing $180 million budget, exclusively to those critical hubs.
This is the high-leverage move. You take money away from the less critical peripheral systems, and you focus it where the network science tells you the vulnerability is. And the breakdown is clear. $12 million for diesel propulsion, $10 million to power generation, and $8 million to C4ISR. That leaves $144 million for everything else.
And what does that focused, fiscally neutral reallocation actually buy them? What's the outcome?
The projected outcome is massive. Availability restored to 70-75% within 12 to 18 months. And most critically, the probability of a catastrophic hub failure is reduced by 78%. It drops from an almost certainty of 0.68 down to just 0.15. Using the network's own topology against its inherent weakness.
That is just incredible efficiency, a huge gain for $0 extra. But the sources did raise one crucial caveat, something about mandatory fixed costs.
Right. The crucial caveat is class society compliance. These are the mandatory inspections to keep the ship certified as seaworthy. This eats up 8 to 12% of the budget. If that mandatory cost isn't funded separately or waived, it creates a shortfall within that reallocated $180 million. If they can't pay for compliance, they risk losing their certificate, and that means 0% availability no matter what. It's a non-negotiable cost.
Assuming they can ring-fence those costs, the overall financial picture is incredibly positive. They avoid a massive costs blowout down the line.
Absolutely. By intervening now, they restore capability within the existing budget. They avoid that chronic deferral path, which the analysis showed was heading toward $2.4 to $2.5 billion cost escalation over 10 years. They're potentially saving $500 or $600 million, and they stop the need for those future emergency funding injections.
So that reallocation is the big mechanical fix, but it can't solve all the systemic problems alone. What other strategic steps were recommended alongside it?
The report lays out 3 parallel tracks. First, the workforce. Commission a program to actually recruit and train the missing 40 to 60 Navy technicians. Restore that organic capability. You can't rely on contractors forever.
And second, speed up the bureaucracy that's slowing down the repairs.
Process streamlining, yes. They have to review that RPR resolution process, cut the average duration by 20-25%. And that's vital, because if you can do that, you can clear the current backlog of 223 defects in 24 to 30 months instead of 4 to 5 years.
There's finally a governance mechanism to make sure the new strategy actually stays on track.
Establishing a cross-functional implementation team. Navy, the sustainment group, finance, all with delegated authority to make tactical decisions and report quarterly to senior leadership. It ensures accountability.
So this whole analysis really provides a roadmap. It moves away from reactive funding, just throwing $300 million at the problem, to proactive, predictive maintenance, all driven by understanding these critical hubs.
And crucially, this framework shouldn't just stop with the LHDs. The report suggests extending this methodology to the entire defense maritime portfolio, frigates, submarines, other complex platforms, to proactively find these same systemic risks before they trigger a catastrophic failure.
So we started this deep dive with Australia's premier amphibious fleet stuck at less than 60% availability. We found the root cause wasn't poor management, but structural underfunding that went back more than a decade.
And the key takeaway, I think, is that the solution wasn't finding new money or just reorganizing again. It was using an abstract mathematical tool network science to find the highest leverage points in the system. By reallocating a small slice of the existing budget, they could achieve a 3x increase in platform resilience. It's a fundamental shift in how you should manage complex sustainment.
It really makes you wonder, doesn't it? If the LHDs operate as a scale-free network, so vulnerable to these sudden, non-linear collapses from neglecting just a few hubs, what other big, complex systems in our daily lives, critical infrastructure, public transport networks, maybe even healthcare systems, are similarly one critical, underfunded hub failure away from a disproportionate, catastrophic collapse? That's something to mull over.